Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using NIME. In this chapter we're going to be talking about support vector machines, or SVMs. Now when I first began studying data mining techniques, I have to admit that the support vector machine, or SVM, was one of the most difficult for me to learn because I was a pound puppy. I didn't have somebody teaching me how to do it through a class. I had to learn it on my own, and it sounded overly complicated, and it took me a long time to piece it together. But I'm going to make this real easy on you. So here's the textbook definition. A support vector machine learns a hyperplane to classify data into two classes. So at a high level, SVM performs a similar task like the C4.5 and the CART decision trees, except that SVM doesn't use decision trees at all. It uses something very different. And the concept of a hyperplane sounds very complex, and trust me, it's actually really not. The math formula behind it is quite complex, but as usual, NIME hides that from me. I don't have to know the formula. Okay, so a hyperplane is just a function like we've done with all of our other line functions, except it's in 3 dimensions. As it turns out, SVM performs a little trick to project your data into higher dimensions. So instead of just a 2-dimensional plot, it raises it into 3 dimensions. And once in 3 dimensions, instead of putting a line in between your predicted wins and losses, it puts a plane in 3 dimensions in between. And it figures out the best plane, which can be curved and shaped very oddly, to separate the data into the 2 classes. So let's start with an example. Let's say that we have a bunch of red and blue balls and we put them on a table, flat surface. Now, if the balls aren't too mixed together, you could put a stick in between them to separate the reds from the blues. And when a new ball gets added that's it's not colored, you don't know it, you would judge based on which side of the stick is that a red ball or a blue ball based on the side of the stick it was going to be on. Now, what do balls on a table and the stick represent? Well, the balls represent data points, and the red and blue color represents the 2 classes, in our case, wins and losses that we've been covering. So the stick represents the hyperplane, which in this case is just a line because it's only in 2 dimensions. But again, the coolest part here is that SVM figures out the function for the hyperplane. You don't have to do that. Okay, but what if the balls are mixed together and a straight stick isn't going to work? I need a workaround. Well, if you quickly lifted up the table, which would raise and toss all of your balls into the air, and then while the balls are in the air in just the right way, you'd use a large sheet of paper to divide the red balls from the blue balls, or the wins from the losses. And is this cheating? No. Lifting up the table is the equivalent of mapping your data into higher dimensions, going from 2 dimensions to 3 dimensions. And this is a mechanism that's very valid for dividing your data. So how does SVM do this? Well, by using a kernel, we have a nice way to operate in higher dimensions. The large sheet of paper is still called a hyperplane, but it's now a function for a plane instead of a function for a line that you would see in like regression. This is going to be best viewed honestly for the next. Now let's take a look at this visually, graphically, so you can understand what the support vector machine is doing. Let's look at a linear example of this. I've got a group of balls on the table, and there are red balls and there are blue balls. And what I want to do is create a function that separates the red balls from the blue balls. In this case, the function can actually be quite simple. It can be a straight line. It's going to be a regression function. And so I'm going to add that to my and I can now see a clear divisor between red and blue. So when I add a new data point to the table, a new ball has been added, and I represent it by the color green. The question is this new ball blue or is it red? The probability is, based on the location in relation to my function line, it would appear to be a blue ball. So let's see a nonlinear example of this. Now the balls are a little bit mixed together here. And so what I need to do is, instead of a regression line, I'm going to use a nonlinear function. And so I can add this equation for a nonlinear line that divides the red balls and the blue balls. And with that function in place, again, I'm now going to add a ball of undetermined color represented by green. And again, if I'm going to bet the probabilities based on the locations, that additional new data point, I believe that point to be blue. And this is still staying in 2 dimensions. Okay, now the balls are completely intermixed like this together. Now what do I do? If I were to draw a function, if you were to build a function that could actually separate a single line in 2 dimensions, it would separate the blues from the reds, that would be the very classic definition of overfitting your model. It memorized the data, it didn't learn a pattern to them. So I can't work in 2 dimensions with the data in this format. So voila, the introduction of support vector machines. So now, map my same blue dots and red dots, but instead of putting them on a table, I raise the balls into 3-dimensional space. So in this case, I've actually raised the blue balls higher than the red balls. Now, with a support vector machine, instead of a line function, I can do a plane function. And I can introduce a hyperplane that separates the red balls from the blue balls in 3-dimensional space. Now, when I add a new data point, again represented in green, instead of which side of the line it's on, I'm now simply estimating which side of the plane is it on. And if it happens to exist, in this case, I would again bet that that data point is blue based on its placement with the rest of the blue data. This is what a support vector machine does. This is when it says creates a hyperplane, it raises the data in 3-dimensional space and then creates a plane that separates the data. So a ball on a table has a location. That can be specified in coordinates. For example, the ball could be 20 inches from the left edge and 50 inches from the bottom edge, which would allow us to describe that ball's location as XY coordinates, or like 20, 50. And that's for a 2-dimensional location. But let's say we go back to our statistics examples and we were using the donor data set. And for each donor, I had various measurements like their age, their gender, their race, their net worth, income, etc. Each of those measurements is a dimension. The bottom line is SVM does it by mapping them into a higher dimension and then finds the hyperplane that separates them. So while I can easily explain this as a 3-dimensional data set, it obviously becomes much harder when it becomes n-dimensional. But again, this is the great part. You don't have to understand that. That's not your job. All you have to know is the support vector machine is going to have a learner and a predictor, and the learner is going to calculate that plane for you. And once the plane has been computed, plugging in any new coordinates into a trained hyperplane, we'll just see which side, in other words, class, a new data point resides. And that's how the support vector machine predictor is going to choose, a win-loss based on which side of the plane you're on. What you'll see is in the SVM learner, what it's trying to do is maximize the margins between the 2 groups. The margin is the distance between the hyperplane and the 2 closest data points from each of the respective classes. So in the ball and table example, the distance between that stick and the closest red ball and the closest blue ball is the margin. For SVM, it's trying to maximize the distance of the margin so that the hyperplane is just as far away from the red ball as it is from the blue ball. And it's in this way that it decreases the chance of misclassification. So why is it called SVM, Support Vector Machine? Well, using the ball and table example, the hyperplane is equidistant from a red ball and a blue ball. These balls are the products of points are called support vectors because they support the hyperplane, and hence the name of the model. Now the calculation of the hyperplane is actually accomplished by what will be called the kernel. There are many of them on the market today. And while they all do the same thing, they accomplish it with completely different mathematical approaches. Their job, they're all doing the same thing. They're trying to compute a hyperplane, but they have a different mathematical formula. And there is no one kernel that's best for any individual solution. You need to try some of them with parameter optimization loops on the key parameters in order to find the best one for your data. Choosing the right kernel is going to be incredibly important because if you don't, the transformation is incorrect and the model is going to have very poor results. So a couple of rules of thumb. If you have linear data, use a linear kernel because it's far less complex. If you go with the RBF, the kind of standard kernel that most people go with, as complexity grows with the size of the training set, and not only is it more expensive to train the kernel, but the projection of this into an infinite number of higher dimensional space is going to be more expensive in terms of computational time. And finally, it's much easier to overfit a complex model than it is a simple one. So keep it simple is always best. Now, different NIME nodes support different kernel availability. The principal node you're going to use, the SVM learner, supports a polynomial, hypertangent, and RBF, the radial-based function. RBF is one of the most common, the ones I usually start with. But it does not support a linear kernel, so that's not available. However, if you can convert over to the Spark, if that's a possibility for you, Spark, the SVM learner, is a linear kernel. And finally, there's one that is the libSVM. It's a connection to a third-party library of SVM functions. So it provides a wide array of additional parameters and things. So you're calling, it supports support vector classification, support vector regression, and distribution estimates, which is one class SVM. So lots of different versions, and within those types, there's all of those kernels, linear, polylit. So the point being, you have to figure out which one of these nodes is going to work for you based on the data type you have available and how deep you want to get into the mathematical understanding. The problem or issue for me is the reason so many people work with NIME is they don't want to get deep into the mathematical functions and choose which mathematical function works. We want to use a parameter optimization loop and flip through these and make a decision based on which one produces the best results. Now, one of the parameters, regardless of which kernel you choose, that you're going to have to ask is the overlapping penalty, or C value. And it's useful in cases that the input data is not separable. In other words, it determines how much of a penalty is assigned to each endpoint that is a misclassification, meaning after the hyperplane has been created, if there's data on the other side, like with our red marble, blue marble example, if there is a blue marble on the red side, how do we want to handle that? When you use a larger value on the overlapping penalty, the optimization will choose a small margin hyperplane. Remember, we talked about margins. it will do a small margin hyperplane if that hyperplane does a better job of getting all of the training points classified correctly. Conversely, a small value will cause the optimizer to look for a larger margin separating the hyperplane, even if that hyperplane misclassifies data points. Take a look at the example you have below. With a low overlapping penalty, there's a slight angle you can see to the line, the hyperplane that's dividing the blue O's and the red X's. Now with a large margin, by maximizing that margin, we've got the line there. That's the margin between the O's and the X's is quite large. If we minimize that margin by having a high overlapping penalty, that forces the line. It makes sure that we keep everything, nice and tight. But it's, it guarantees that I'm not going to misclassify data. So this is, again, a perfect candidate for a parameter optimization loop to say, I'm going to flip through different values of the overlapping penalty to see where I get the best sensitivity for the value I'm looking for. All right, let's look at, I've got two examples here of the support vector machine. And starting with the first one, let's remind ourselves, I know you've seen this if you've been taking the entire class, but maybe you're just looking at this one video. So I'm going to remind you of what the data looks like. We're trying to predict the opportunity result out of all of this categorical and continuous variables that are set up, and trying to understand whether they're going to win or lose. And I always partition 70% for training and 30% for testing. Now in the support vector learner node, go ahead and call this up. Now I tell it that I want the opportunity result, and that's the column, that's the classification. Then I'm computing and entering a good starting point for the overlapping penalty is going to be 1. And then you're going to have to choose the kernel and any parameters that are on the kernel. So what I would again suggest you do going forward is once you've chosen your kernel, you'll alter the parameters using a parameter optimization loop to find the best final fittings. But you might want to just start with the default values, run a polynomial, a hypertangent, and an RBF. See what you get. One of them is going to be significantly better than the other. Then run your loops against it to say, if I've got two parameters here, I'm going to have a loop within a loop. I'm going to change the kappa and I'm going to change the delta, and I'm going to come up with a value for them. So for example, if I've just got one value, like here for RBF, I'm going to probably run this from 0.1 up to 1 by 0.1. So I'll run 10 iterations and I'll see which one produces the best result. The problem with the support vector learner is that it's time intensive. Even though in my case, let's see, I've got 54,000 rows, this learner probably took 2 to 3 hours to run, and I've got a fairly beefy machine that it's running on. So it was not quick. Now, in the predictor, there's nothing special about the SVM predictor. Like usual, I'm just specifying I'm predicting the opportunity result. So there's nothing unusual about this setup. And then finally, let's look at the scorer and the accuracy. Now, for those of you, for just a reminder here, if you're not familiar with how to interpret and understand the accuracy, you can turn to chapter 59 on decision trees, where I spend about 30 minutes walking through in great detail the confusion matrix and true positives, false positives, and how we compute sensitivity and specificity and accuracy and so on. So I'm not going to go into that in this chapter. So again, if you need help with that, go to chapter 59 and watch that video again to explain how to score and how to interpret these scores. But what I'm going to look at right away is, look at this. Isn't it marvelous? I'm on my wins. I've got sensitivity up to 99%. Isn't that fabulous? It means 99% of the time it identifies a win. The problem is the losses are 0.002. In other words, it pretty much guessed everybody was a win. And by doing so, they always got the wins right, but they didn't get any of the losses right, which is a terrible. So even though sensitivity was exactly where I would have loved to seen it, the overall model accuracy is only 22%. Now there's a reason for that, partially because I didn't take all of the categorical data. I came up with two things that remember we did for k-nearest means. First off, I added a normalizer. Okay? So I took all of the numeric columns that you can see here, and then I set them to a min-max optimization of 0 to 1. That, remember, that minimizes the impact of large numbers versus small numbers. So taking something like age and salary and comparing them together in the same model. This brings them all to a normalized range. The other thing I did is all the one-to-manys. I replaced all of the categorical data with numeric data because the support vector machine doesn't support categorical data. So all of those columns would have been dropped. They were dropped in the top model. Of course, I exclude opportunity result because I don't want to replace that with a category. That is the result I'm trying to reach. Now, I do my partitioning. And in this case, just for fun, I actually changed it and I did an RBF with a sigma of 0.1. And my score node this time through, when I look at the accuracy statistics, this time I've got my sensitivity to a win at least up to 0.13%. It's still not particularly good, obviously. The sensitivity of a loss is great. The overall model accuracy is still great because we don't win very many. But as a rule, this ability to pick a win is not doing very well at all. And had I looked at this any further, I would have said there's no point in me going on to try and tweak these parameters because support vector machine and this particular data set does not appear to be doing very well. And I'm doing so much better with random forests that I'm going to stop here. So again, I can see the results of each of my, as I'm doing all the comparisons of all my various models that I built, starting with the trees. And now I've updated the chart to include the support vector machine with its less than impressive results that have me saying it still hasn't knocked out my front runner. So an SVM is a support vector machine, and it creates a hyperplane to classify data into two classes. The 3D space is used to solve the problem of nonlinear equations, where we map the data into three-dimensional space. That completes this chapter of the class. Feel free to move on to the next chapter.